16.2, line integrals. So the general idea here is to take the integral over curves instead of line segments. So in this section, we define an integral that is similar to a single integral, except that instead of integrating over a straight line segment, which is an interval, we integrate over a curve C. These integrals are called line integrals, or you might say it's just curve integrals. So what are we going to do? We're going to take C as our curve, and we use parametric equation of the curve to represent the curve. So x is a function, depends on t. Y is a function, depends on t. And t is just a new variable, independent variable, ranges between a and b. Remember that in physics, we usually say that t is time, and x as a position, y as position of the particle or the object depends on time. Or equivalently, by the vector equation RT, which is nothing but xt in the direction of x-axis plus yt in the direction of y-axis. Or remember that you can generally just say that RT is nothing but vector xt, first component is xt, a function, a second component, yt is another function. And suppose that C as a curve is smooth curve. What's the meaning of that? It means that you can take the derivative of that function, and that derivative is continuous, and the derivative is never zero. So how do we just take the integral? Remember that here you have a curve. We can divide this curve into very small pieces, small line segments, connect them together, and actually define this curve. We are actually using the Riemann sum. So to define the integral of function f on a smooth curve C, we can define the line integral of f along C as the integral f of x and y ds over C, which is nothing but the limit of the Riemann sum while n goes to infinity. And remember that if the limit exists, you say that, hey, the integral, line integral of f over C exists. So what is S? Remember that we're dividing this curve into small pieces, very small sub-intervals. Xi is x at time ti, yi is y at time ti, and corresponding points pi, xi, yi divide curve C into n subsets of very small line segments with length delta S1, delta S2, and delta Sn. So here you have sub-arcs. This is your curve itself, and these little sub-arcs, when n is very small, are actually just some line segments. Remember, when we're talking about parametric representation, T ranges between A and B. Ti star, for example, is time between Ti minus 1 and Ti, and the position of your object or your particle is between these 2 points. So when you have Ti star, the position of this particle is nothing but at the point Pi star with components Xi star and Yi star. Very well. Let us make it in the format that we can actually use it. The line integral of function f along with curve c is equal to the integral a to b f at xt yt times square root of partial derivative of x with respect to t squared plus partial derivative of y with respect to t squared. And now, instead of having just ds, we have dt. This whole expression here is your ds. Very well, let us go over some examples to see what's going on. Case 1. Suppose the parameterization for the curve is given, so you don't have to do anything else. Question says evaluate the integral of function 2 plus x squared times y along with curve C, where curve C is upper half of a unit circle. So for sure, you know that you have a circle, it's above x-axis, upper half. Remember, one of the most popular parameterization for a circle is taking x to be cosine t, y to be sine t, and since you are working with upper half, your t, or in this case, your theta, ranges between 0 and pi. Following the formula, the integral of function f along with curve c is equal to the integral. You just copy down the function and substitute cosine t, sine t for x and y, and your ds is the square root of partial derivative of x with respect to t, partial derivative of y with respect to t. Both of these are squared, then add together. Your x is cosine t, so dx dt is minus sine t, and your y is sine t, so dy dt is nothing but cosine t. Lower limit is 0, upper limit is pi, and we calculated the partial derivatives. We just substitute these here and try to simplify before taking the integral. We already know that sine squared plus cosine squared is equal to 1. Square root of 1 is 1, so you're not worried about this expression here. We're just taking the integral of 2 plus cosine squared sine with respect to t when t ranges between 0 and pi. So the first integral, integral of 2 dt is just 2t. The second integral, you can use u sub, integral of cosine squared sine dt. You can say that, hey, I want to take u to be my cosine. The integral of cosine is negative sine, so this is minus integral u squared du. So here you have negative a third u cubed, and your u is just cosine. So you get cosine cubed of t. That's how you get cosine cubed down here. Then you plug in pi, then you plug in 0. Try to simplify as much as you can. The final answer is 2 pi plus 2 over 3. Second case, the parameterization for the curve is not given. Very well, let's take a look at an example, see what's going on. Here you have the integral of 2x ds, where c, or the curve, consists of arc c sub 1. The first curve is defined as y equals to x squared from 0 and 0, the origin, to 1 and 1. So let us graph this guy. The first curve, 0, 0, to 1 and 1, and it stops here. So this is your c sub 1, which is y equals to x squared, followed by the vertical line segment c sub 2, which is just a straight line connecting 1 and 1 to 1 and 2. So this is the second curve, just a straight line. And C is defined to be the union of these two curves. So our goal is to find this integral. Perfect. Let us calculate the integral along with c sub 1. So integral of 2x c sub 1 is equal to, note that y is equal to x squared. You can take x to be t, so y is equal to t squared. And t ranges between 0 and 1. T is equal to x. My x starts from 0 and stops at 1. X starts at 0, stops at 1. So my t ranges between 0 and 1. The first integral is integral of 2t, wherever we see x, we plug in t, times square root of partial derivative of x with respect to t, which is 1, we raise it to 2, plus partial derivative of y with respect to t, which is 2t squared. So this integral, the first integral along C1, is integral 2t square root of 1 plus 4t squared. And t, or just x, ranges between 0 and 1. We can use u sub. You can take u to be 1 plus 4t squared du is 8t dt. So since you have 2, you can multiply it by 4, divide it by 4. So here you have 1 over 4 integral square root of u du. So since u has exponent a half, you add 1, you divide by 1 plus a half. So if you simplify this, you get 1/4, 2/3, 1 plus 4t squared raised to 3/2. T ranges between 0 and 1, plug in 1, then plug in 0, do the algebra, you find the line integral along with c sub 1. Now, on c sub 2, you just have a vertical line. Your x is fixed, your x is just 1, but your y ranges between 1 and 2. So we can use parametrization. X is fixed number equals to 1, and y is just ranges between 1 and 2. So let y to be t. The integral of the function along with c sub 2 is nothing but integral. Your t ranges between 1 and 2. You have 2 as the constant, and x is equal to 1. So we plug in 1 for x. Then for ds, we have the square root of dx over dt squared plus dy over dt squared. Since x is constant, the derivative is 0. Y is t, the derivative is 1. So you get square root of 0 plus 1 squared, which is square root of just 1, which is 1. So you can forget about this expression here. You are taking the integral of 2 dt, t ranges between 1 and 2. This guy is equal to 2t, t ranges between 1 and 2, which is 2, 2 minus 1, or 2. The first integral, the second integral, if you add them together, you have the integral of the function along with these two curves, which is c sub 1 union c sub 2. This is the final answer. Let's make it more interesting. Let's go over another example here. Evaluate the line integral where c is given as curve below. So here you have the integral of x minus 2y squared dy, and c is the arc of the parabola y equals to x squared that connected -2 and 4 to 1 and 1. We can use the usual parametrization. We can say that, hey, my x is x, my y is equal to x squared. So wherever I see y, I can write x squared. I have the integral -2 to 1, x minus 2y squared, which is x minus x squared to the second power, x to the fourth. And now your ds, which is dy, is equal to 2x dx. Very well, x ranges between -2 and 1, and here you have a nice function. You distribute 2x into parentheses, you get 2x squared minus 4x to the fifth. Then you take the integral and plug in 1, then plug in -2, and the final answer is 48. Another example, evaluate the line integral for given c. So here you have the integral of x times square root of y dx plus 2y square root of x dy. And curve c consists of the shortest arc of the circle, unit circle, x squared plus y squared equals to 1, from 1 and 0 to 0 and 1, and a line segment from 0, 1 to 4 and 3. We can visualize this curve, union of two curves. C sub 1, for example, is the circle connecting 1 and 0 to 0 and 1. Then you have line segment connecting 0, 1 to 4 and 3. So your C consists of two parts. One part along C sub 1, which is some part of the circle, and C sub 2 is just a nice line segment. Very well. On C sub 1, since you have a circle, you can say x is cosine t. And dx is equal to negative sine t dt. And as usual, y is equal to sine t. So the derivative of y, or y prime, is equal to cosine t dt. And note that your t ranges between 0 and pi over 2. On the second part, x is equal to 4t. You have to write equation of the line passing through these 2 points. So you can say, hey, y is equal to mx plus b. My m, or the slope, is equal to 3 minus 1 divided by 4 minus 0, or 1 over 2. So my y is equal to a half x plus b. Let us plug in 0 and 1. 1 is equal to a half times 0 plus b. So b is equal to 1. So equation of the line is a half x plus 1. This is your line here. Well, since x ranges between 0 and 4, x is 40. If you plug in 0, 40, x is 0. If you plug in 140, your x is equal to 4. So take a look at this. T and x. T is 0, your x is 0. T is 1, x is 4. Now you can use your x to simplify your y. Y is equal to a half 40 plus 1. So y is 2t plus 1. So here we're using these two parametrizations. X is 40, so the derivative of x is 4 dt, and y is 2t plus 1, so dy is 2 dt, and t ranges between 0 and 1. Very well. Now that we have these two curves and line segment, we can divide the integral in halves and start taking the integral over these two subcurves. So the first one is x square root of y dx plus 2y square root of x dy over c sub 1, the first integral, plus the integral x square root of y dx plus 2y square root of x dy over c sub 2. Over the first curve, we know that our t ranges between 0 and pi over 2. Our x is cosine t. Our y is sine t. So you have negative cosine t, sine t 3/2 plus 2 sine t, cosine t raised to 3/2 dt. You can use substitution. You can take y as sine t dy, which is cosine t dt, next to it. Then square root of u, the integral. So the integral of square root of u is the integral of u to a half, which is 1 over 1 plus a half u2 1 plus a half. So you get 2 over 3, u2 3 over 2. That's how you get the exponent here. Then plus the second integral. Now for the second integral, your y is defined as 2t plus 1. So 2t plus 1, and x is 40 plus 2y, 2 times 2t plus 1 square root of 40 dy. Remember that here you have dx and dy. You have to substitute for dt for dx and 2 dt for dy before taking the integral. So after taking the integral, you have just negative 2/5 sine t to 5 over 2 minus 4 over 5 cosine t to 5 over 2. T ranges between 0 and pi over 2, and the second integral is 16 over 3t, 2t plus 1 raised to 3/2 minus 16 over 5, 15, 2t plus 1 to 5 over 2 plus the last one, which is 8, 4 over 5, t to 5 over 2 plus 2/3, t 3 over 2, 0 to 1. After doing the algebra, you have the integral of this function over the union of these two curves. Line integrals in space. Now suppose you have a curve in three-dimensional space. So of course you can use parametrization, xt, yt, zt, and then take the integral of the function along curve C, which is integral of f of x, y, z along curve C, ds. So your ds is going to be square root of partial derivative of x with respect to t squared plus partial derivative of y with respect to t squared plus partial derivative of z with respect to t squared. If you use vector equation of your curve, then the integral can be written f of rt, absolute value of the derivative of vector equation of the curve dt. T ranges between a and b. Take a look at this example. Suppose you want to take the integral of function y sine z along with curve c. Curve c is defined as circular helix given by the equations x equals to cosine t, y equals to sine t, and z is equal to t. T ranges between 0 and 2 pi. So this is the curve that you have. And you are taking the integral of this function y sine z along this curve. Let us follow the formula. The integral of y sine z ds is nothing but the integral of sine t. Your y is defined as sine t, so you substitute it here. Sine z, z is t, so instead of z, we use t, and ds, which is square root of partial derivative of x squared partial derivative of y squared plus partial derivative of z squared. Partial derivative of x is negative sine t. Negative sine t squared is sine t squared plus partial derivative of y with respect to t, which is cosine squared plus partial derivative of z with respect to t, which is 1 squared. Sine squared plus cosine squared is nothing but 1, so you get square root of 1 plus 1, or square root of 2, times the integral of sine squared. So to take the integral of sine squared, we write it as 1 minus cosine 2t divided by 2. Since you have exponent 2, your goal is to reduce this exponent, so let us use 1 minus cosine 2t divided by 2. Then dt. So here you have square root of 2 divided by 2. Then take the integral of 1 with respect to t is t, minus the integral of cosine 2t is a half sine 2t. Since you have subtraction in between, you have your subtraction, then you plug in 2 pi, then you plug in 0. Don't worry about 0, you have t, and sine 0 is just 0. So just plug in 2t to have the integral of this function along this curve, which is square root of 2 pi. Finally, let us have this definition. Let f be a continuous vector field defined on a smooth curve C given by a vector function Rt. T ranges between a and b. Then the line integral of the vector function f along C is defined as f inner product dr over C, which is equal to the integral f evaluated at Rt inner product r prime t dt. T ranges between a and b, which is equal to nothing but the integral of f inner product t along C. Let us go over one example, see what's going on here, how we can apply this new definition. Example, find the work done by the force field F equals to x squared and negative xy, moving a particle along the quarter circle RT, which is cosine t and sine t, t ranges between 0 and pi halves. Very well. To follow the formula, the integral of function f inner product dr is equal to the integral when you evaluate function f at rt inner product r prime of t dt. So first, substitute rt into function f. So your x is cosine, your y is sine, f of rt is x squared, which is cosine t squared, and negative xy. Your y is equal to sine t, so cosine times sine is the second scalar function with respect to t. So as you know, here you have a vector, cosine squared. And the second one, second component is cosine t, sine t. The derivative of r is equal to the derivative of cosine, which is negative sine. So you have negative sine t, comma, and the derivative of sine, which is cosine t. You have two vectors. To find the integral, you have to find the inner product between them. So you multiply the first components, you multiply the second components, and add them together. So f rt, inner product, r prime of t, is equal to negative sine t cosine squared of t plus, since you have a negative sign, plus minus cosine squared of t times sine t. If you add these together, you get negative 2 cosine squared t sine t. Now you can easily take the integral by using u sub. Let u be cosine t, du is negative sine t dt. So negative sine t dt is du, so you have a third cosine cube. T ranges between 0 and pi over 2. Don't forget your 2. After simplifying this, you get the work done, which is equal to negative 2/3.